Okay, so we've been talking about triangles and things about triangles. Okay, so anyway. Talk about classifying triangles. There's two ways to really refer to a triangle. We can refer to them by their angles, in which case we go by the largest angle. Or we can refer to them by their sides. If we refer to triangles by their angles, we can start out with a triangle. It looks something like this. All of those angles are less than 90 degrees. Those are called acute. So the largest angle in that triangle is still an acute angle, so it would be an acute triangle. Bring up. We have a triangle that can have a right angle in it. Of course, that would be called a right triangle. Now, if there's a right angle in a triangle, how do we know that that has to be the largest angle? Well, what do the angles of a triangle add up to? 180. But the three angles of the triangle have to add up to 180. If one of them is 90 degrees, that only leaves 90 degrees left for the other two angles. So the other two angles have to add up to 90. So nothing can be bigger than 90 if there's 190. Then, of course, the third option to have an obtuse angle. And of course, an obtuse angle is bigger than 90 degrees, so there's no way you can have a second obtuse angle, because there's going to be less than 90 degrees left out of our 180. For sides, let's start with the most special first. Those little hash marks mean that those sides are equal. That would be called what kind of a triangle? Lateral, you got it. Equal meaning equal, lateral meaning side. We have a triangle where two sides are the same, so those single hash sides are the same, the double hash one is different. Well, this isosceles, very good. And of course, we have a triangle where all the sides are different. You know the name for that one?
Scalene.
Oh, I'm like the first person in 2 years that knew that word. Scalene is correct. So none of the sides are the same. Now, often when we name a triangle, at least for certain types of triangles, we will use both the name for the sides and the angle. Mostly for isosceles, occasionally for scalene. Obviously, for equilateral, we can't do it. An equilateral triangle, of course, is always acute. Why does that have to be? Well, one rule in a triangle let's look at our angles here. Let's say this angle over here, let's call it 31 degrees. Let's call this one here 102 degrees. What's this angle up here have to be? We're close. 57 degrees. To make that add up to, actually, no, not 57. 47, thank you. To make that add up to 180 degrees, it has to be 47 degrees. Now, if I label my angles A, B, and C, which side has to be the longest? AC, AB?
BC.
Longest. GA.
Oh,
Yeah.
shit. Yes.
Why is that the longest side?
Well,
Well, not hypotenuse, but it's, what's that word?
Because it is.
Because it is. Well, it looks like it is, yes. But the longest side will always be opposite or across from the largest angle. So 102 is the biggest angle. The biggest side has to be the side across from it. By opposite side, I mean the side that doesn't touch the angle. These other two sides here touch that angle. The other side is the opposite side. Then, of course, the smallest side would have to be that is opposite the 31 degrees, the smallest angle. So that brings us back to an equilateral triangle. Which angle has to be the smallest? Oh, they're all the same because the single arc means that those angles are. They're all the same because the sides across from them are all the same. If one angle is bigger than the other, the side across from it would have to be bigger than the other sides. And that can't be in an equilateral triangle. So an equilateral triangle is always acute and all the angles are always same and they add up to 180. But we could have this. If I'm naming it by the sides, what is that? After by the angles, it would be a right angle. By the sides, it would be isosceles. So that would be called an isosceles triangle. I have this situation. That would be called what? Acute isosceles, or isosceles acute. Bless you. Thank you. You might have this one. That be called lean right triangle. I'm just going to stop at scalene and right.
Sounds good.
Of course, this one would be called isn't obtuse isosceles. Just throw stuff at him until he does. So let's talk a little bit more about that angle sum, where it comes from and how we know that's the angle sum. We're going to do this. We're going to start walking in a single direction, or moving in a single direction. And we're going to get to a point and we're going to turn. What do I, if I call this angle A and this angle out here angle D? What do I know about those two angles? That's 180. I'm going in this new direction and I'm going to stop there and I'm going to turn again. I'm going to call this angle here B and this E. What do I know about angles B and E? Also add up to 180. Now when I get down here back to this original corner, I'm going to turn. So I'm going back in the direction I started. We'll call this angle C and F. Of course, angles C and F are up to 180. So if I just add those up, all of those angles together, A plus B plus C plus D plus E, F, add up to 540 degrees. But started out in this direction and we turned all the way around, coming back in that direction. How far did we turn? What angles describe the turn? F, right? Mm-hmm. Plus E plus F, 160 degrees. Come over here and I subtract D, F, I've subtracted 360 degrees, right?
Yep.
D, E, and F are gone. All that's left is A, B, and C. 540 minus 360 is 180 degrees. So we're left with the internal angle sum of 180 degrees. Well, is that true of every figure? It's true of every triangle, but is it true of every figure? Sort of. Let's look at something with 4 sides here. So if I start walking down this side here, and I turn, right? Call that angle E, A. Of course, that adds up to 180. Let's do B and F. Those two add up to 180. Call this C and E. Add up to 180. And then, of course, in H, add up to 180. Now we have all of those together. Add up to how much? 80, 180, 180, 180 times 4, which is 720 degrees. But the angles on the outside still only make one complete turn, a 360. So if I subtract those angles off, I'm only still subtracting 360 degrees. I've got A plus B plus C plus D, 360 degrees. So a 4-sided figure is 360 instead of 180. Well, notice what happens is every vertex, every corner of that figure, put 360 degrees into that total. But then each time I subtracted, each corner put 180 degrees into that total. But then each time I subtracted a total of 360 degrees for those exterior or outside angles. Angle sum of any figure. Going to be the number of sides, 180 degrees, and then subtract 360. Some textbooks shorten this. It has 180 times the number of sides minus 2, because 360 is just 2. Excuse me. 360 is just 2 180s, so they shorten it to that. But the top formula makes more sense to me because that shows where it comes from. That is more powerful than you might imagine. Looking at figures, being able to find those missing angles, know all of them but one, or even in some cases, if you know just one of them. If I tell you that this angle up here, 28 degrees, can I find this angle right here? How? So there you go. If we look at those angles have to be the same. So 2x plus 28 has to add up to 180. We could solve that equation. Or we could have just said 180 degrees minus the 28 degrees that we know is 152. Divide that by 2 to get 76. Questions? Let's go the other way. What if I tell you that this angle here is 31 degrees? This one, what do I do? Okay, there we go. This time, this one's also 31 degrees. So 31 times 2 is 2. We subtract that from 180 to get 1. Not so bad. So we've talked about similar triangles. If this is a right triangle and this angle here is 35 degrees, what's this angle up here? 55. 180 minus 90, right angle would be 90. Minus 35 more would give us 50. Now, what if I have another right triangle over here, and this has an angle here of 35 degrees? What's this other angle have to be? 5. Well, we said similar triangles are just triangles that have all three the same angles, right? They don't have to be the same orientation. They can be flipped, they can be rotated, or whatever. They're still similar. Well, what this is showing us is that in right triangles, we have the right angle. If we know that one of the other angles is the same, the third one must be because they add up to 180. Which means when I have right triangles, anytime I have one of the non-right angles equal, those must be similar triangles. Which leads us to some really kind of interesting things. For those of you that can't catch that, sorry. In a triangle, if I draw a line from a vertex to the opposite side, so that it intersects at a right angle, that is called an altitude. From a vertex and perpendicular to the opposite side. If I draw a line from a vertex to the opposite side, so that it cuts the opposite side into two equal pieces, that's called a median. From a vertex, cuts opposite side in half. Third possibility, go from a vertex and draw a line that cuts the angle in half. That is called an angle bisector. Cuts the angle in half. Well, we've got some special triangles that we've looked at so far today. Let's look at how these three things apply in those special triangles. Now we're going to start by looking at isosceles triangles. Here's an isosceles triangle. You know these two angles have to be equal because they're across from equal sides. We're going to focus on this vertex right here. The vertex in the equal angles. First, I'm going to start off with an altitude. From that vertex to the opposite side. Now, the altitude has to do what when it hits the opposite side? Draw that down, it makes a right angle. Now, down here, this, of course, is a line. If this is 90 degrees, what's this angle have to be? 90 degrees. So if two lines intersect, if they form a 90-degree angle on one side, they have to form a 90-degree angle on the other side. So both of those angles are 90 degrees, which means this angle and this angle are the same, doesn't it? How about this angle related to this angle? They're still the same. They haven't changed, have they? Have they? Well, if two of the angles are the same, what does that tell us about these angles? They're the same. So that altitude has to be an angle bisector. When we draw, if it's an isosceles triangle, if we're working with that vertex between the equal sides, that altitude is also an angle bisector. It has to cut the angle in half. Well, we know that if all three angles are the same, those triangles are similar. This triangle over here and then this one over here have to be similar. Once we know they're similar, all we need is one set of corresponding sides to be equal. And we know they're not just similar, they're actually equal, what we call congruent. Well, this side, by definition of our isosceles triangle, is equal to that side, isn't it?
Yep.
Even more, we have a second side. This side is, of course, equal to itself, right? So 2 out of 3 sides are the same. The third one, again, must be the same. Means this piece and this piece are length. That altitude is also a median. When it hits the other side, it cuts the other side in half. Well, let's take a look at two isosceles triangles this time, just for fun. And let's put in an angle bisector. So, these two angles, of course, are equal to each other by definition. Right? If it's an angle bisector, those two angles have to be equal because it cuts the angle in half. That's into two equal angles. So what does that tell us? If 2 of the angles in the green triangle are equal to 2 of the angles in the brown triangle, what's that tell us about these two angles? Same. 2 of the angles between triangles are the same. The third angle between those triangles has to be the same. Well, those two angles are the same, but they add up to what? 180. I call them x. It would be 2x equals 180. Well, what's x have to be?
90.
Divided by 2, x is 90 degrees. Those are right angles. So that angle bisector is also altitude. Now that we know that's a right angle, and we know those triangles are not just similar, but they are equal again, this side's equal to itself, and this side's equal to that side. What does that tell us about this piece and this piece? Same. So this is, again, also a median. Probably predict what's coming next. Let's draw it upside down just for fun. We've got an isosceles triangle here again. From this vertex between the equal sides, I draw this up so that it cuts this in half. Now, I know that this side's equal to itself. This side's equal to that side, right? And these two pieces are equal to each other because it's a median. So if all 3 sides are equal, then the 2 triangles are equal or congruent. So if they're equal, that means this angle has to equal that angle. So it is bisector. These 2 angles must be equal, but they add up to a straight line, which means they must be angles. Got it, so it's altitude. In isosceles triangles, if we're working with that vertex between the 2 equal sides, median, the altitude, and the angle bisector are the same line. This is what has allowed us, we used this in Unit 1 without really explicitly saying it. When we found the height of those trusses, we knew if it cut the bottom in half here, it had to also intersect the bottom at a right angle. Talk a little more about our right triangles here. If I tell you that this angle over here is, oh, let's call it 7 degrees. What's this angle up here at? 180 minus 90 leaves us with 90 degrees. Minus another 37 would be 53 degrees.
Yeah, way off to 15.
That's okay. I've been a little weird today too on stuff. Now here's what I'm going to do. I'm going to use my vertex from my right angle here. And I'm going to draw an altitude to the other side. It's going to hit the other side at a right angle. First, we know it's a right angle on both sides. Now let's focus on this red triangle here. At 37, this is a right angle. What's this angle? 53 again.
Oh.
Which means that that red triangle is similar to the big triangle. It's got the same angles. Obviously, it's smaller than the big one, but it has the same angles. Look at this blue triangle here. This is a right angle. We got the 53-degree angle. What's this one have to be? 37. So once again, all of those angles in that little blue triangle are the same as they are in the original big triangle. So that little blue triangle is similar to the big triangle. What does that mean? Well, let's take a slightly different picture here. Let's say that this is 8 inches, 15 inches, and 17. You can verify that that's a right triangle by doing a squared plus b squared equals c. I'm drawing altitude across here, like that. Triangle right there. Draw it up here. I'm going to flip it, but I'm going to draw it up here. This is the right angle, right? The one side of that I know, the 8, which side is that? Is that one of the legs or is it the hypotenuse? It's the hypotenuse of that little triangle. What I'm going to do is this. I'm going to label this piece here X. I'm going to label this piece here Y. So which is X, the short leg or the long leg?
Long.
It's in the long. So Y would be the short. Right? This would be that angle there. Now I'm going to draw in the purple triangle here, the bigger one of the two little pieces. Draw it like that. Of course, the only side we know of that is the hypotenuse, which is right angle, so that hypotenuse would be down there. X is one of those sides, short leg in this case. I'm going to call this piece here now I can compare this back to the big triangle here, the 8, 15, 17. I know that 17 corresponds with the 8, doesn't it? I'm looking for X out of this triangle. X is going to go on bottom with the 8. What side does it correspond with from the other triangle?
Oh.
X corresponds with the 15. So I'm going to cross multiply and divide. 8 times 15 divided by 7. You're going to get a little ugly. Gives us X is 7.059. 7.059 inches across here. let's find y. We've still got 17 goes to 8. Y go on with the 17 or the 8? Does the y go with the 17 or the 8? Goes with the 8. The corresponding side from the other triangle would be the 8 from the other triangle, right? So we cross multiply and divide. We've got 8 times 8 divided by 17. Yep, so it's going to be like 3.74 or 765. So y is 3.765 here. Well, let's see if we can finding the missing sides of this other triangle over here. Now we have 17 corresponds with the 15. X goes with the 15. It corresponds with what side from the other triangle? Cross multiply and divide. 15 times 8 divided by 17. 7.059. Good, that's what we had before for X, right?
Mhm.
Well, 17 still corresponds to the 15 for the hypotenuse. Let's look for Z. Z would correspond to 15 times 15. 13.235. $15.5 inches. So two things double check. One, got the same answer for this going both ways. And these two add up to 17. But more importantly, with a right triangle, what did I do wrong? Something didn't happen.
But 18,
It's
so
13 point.
That's 13, not 15. Thank you. I read it off the calculator wrong. It's definitely time, getting close to time to call it a day. I didn't even catch that when I went to add them together to double check.
What do we
So,
introduce?
I was at it, I was like, what are you getting?
When do we get to introduce integrals? Well,
not in this class, we're not going to do integrals.
they're easy.
Once you see the pattern, they're easy. The theory behind them is a little complicated.
We'll go anti-duals. That'll make someone really want to quit math.
So basically, the power of this is if you have a right triangle, you know all three sides, you can always find that altitude of that right triangle. Kind of a neat little quirk of those right triangles. Not even really a quirk, it's just because of the fact that if one angle is the same, one of the non-right angles is the same, all the others have. Okay, so what I'm going to do, I'll have you work on stuff for just a few minutes, and I'm going to pass something out for you. In your big book, page 562, 563, exercise 22-1. 7 through 10 is just going to be identifying some parts. Page 565 through 567, exercise 22-2, 7 through 17, the odd. And this is the last page, one more page there.
2 minutes.
569 through 570, exercise 22-3. 7 through 12, I'll have you all those as well. So yes, identify. And then I've got a packet I'm going to pass out for you guys to play with for a while. You can partner up if you want to work on this.
So,
Together in a group if you'd like.
complementary angles, they add up to 90 or?
Complementary added tonight. Remember, compliments when you're right.
Yeah.
Go.
99.
Didn't expect that on you.
Sure, this would be such angry papers you have.
Like I said, partner up or gather into a group if you'd like.
Looks ugly.
They ask for, each of them asks for like 5 or 6 different things. Some of them will ask for a couple of things. They want you to find in the figure, missing pieces of